Sir.
Narendra Reddy, Government Degree College, Ramanapet.
Okay.
Sir. Welcome to T-Shirt, sir. Today we discuss about the sequence of functions. So myself, Dr. Upender, Assistant Professor of Mathematics, Nagarjuna Government College, Nalgonda, and with my friend G. Narendra Reddy, the Assistant Professor of Mathematics, Government Degree College, Ravanapet. So today we discuss about the sequence of functions. This is a part of the degree second year syllabus. In the last classes, we have already studied the sequence of real numbers. So what is the sequence of real numbers definition? So the how to convergent of the sequence of numbers and divergent, the Cauchy sequence and its properties can be taken. Same the definitions and reciprocal to the sequence of functions is here, right? How the functions definition and everything. So today we will discuss in the chapter is here. So this is the most important topic of the degree second year, the third unit curriculum can be taken, right? The suppose the my friend the Narendra, so will introduce the definition of the sequence of functions.
Thank you, sir. Already we have discussed about the sequence of real numbers in the last class. Suppose a mapping f from n to r is called sequence of real numbers. Suppose A is any non-empty set, then the mapping f from n to A is called sequence on set A. Suppose if A is any non-empty set, then the mapping f from n to A, suppose here 1, 2, 3, 4, so on. Here AB is a codomain of the function f, 1 goes to some a1, 2 goes to a2, 3 goes to a3, so on. In this case, here a1, a2, a3, so on is called sequence on A. Already we have discussed sequence of real numbers in the last class. Suppose if A is set of all functions, here A is set of all functions, suppose here n to A, where n is set of all natural numbers, A is set of all functions 1, 2, 3, 4, so on. Here f1 is the one function, f2 is another function, f3 is another function A, so on. If 1 goes to f1, 2 goes to f2, 3 goes to f3, 4 goes to f4, so on. In this case, the mapping f from n to A is called sequence on A. Here A is set of all functions, therefore f is sequence on A. A means set of all functions, therefore f is sequence of functions. Here f1 is the first term of the sequence, f2 is second term, f3 is third term, f4 is the fourth term, so on. Fn is the nth term of the sequence. In generally, sequence of functions is denoted by fn of x. Here n is equal to 1 to infinity. This is the sequence of functions. Suppose if A is set of all functions f from S to R, where S is subset of R, A is set of all functions, A is set of all functions where f from S to R, S is subset of R. This is the f is a function which is a real valued function. a function f is said to be real valued function if codomain is subset of R or codomain is R. This is called real valued function. Here A is set of all real valued functions, then mapping f from n to A is called sequence of functions of real valued functions. Now here suppose fn of x is sequence of real valued functions which is denoted by n is equal to 1 to infinity. Suppose for example fn of x is equal to x to the power of n, where n belongs to n and x belongs to suppose closed interval 0 1. Now here n is the domain. Now this is the codomain 1 2 3 4 so on. In this case 1 goes to f1 of x, 2 goes to f2, 3 goes to f3, so on, n goes to fn, so on. Here f1 of x is a x, f2 of x is x square, f3 of x is x cube, so on. Here this is one example of sequence of functions. Similarly, we can discuss some examples. My sir, Upender sir.
Sir, Narendra sir, so you explain your definition. So what is the sequence of numbers and sequence of function? Sequence of numbers means one natural numbers are mapped to the numbers. Right. So 1, 2, 3 mapped to the A1, 1 mapped to A1, 2 mapped to A2, 3 mapped to A3. Then that is called the sequence of real numbers. And the same various is here. So same natural numbers domain. So 1 mapped to F1, 2 mapped to F2, 3 mapped to F3. So this is called the sequence of functions is here. So in the numbers, natural numbers are mapped to the numbers is called sequence of numbers is here. And same one, the natural numbers domain is natural numbers mapped to the functions is called sequence of functions is here. So sequence of functions is here generally denoted by sequence of numbers is denoted by xn is here, and sequence of functions are generally denoted by fn is here. So n is natural numbers can be taken. The n is equal 1 2 3 4 can be taken, f1 f2 f3 f4 all are the sequence of numbers can be taken. In the see the first example, fn x is equal to x power n, x belongs to closed 0 comma 1, n is natural number. In this example, so f1 x is equal to x power 1 and f2 x is equal to x square and f3 x is equal to x power 3 and f4 x is equal to x power 4. So f5 x is equal to x power 5 dash dash. This is the sequence of functions is here. So where the what the x belongs to the closed 0 comma 1 domain can be taken, and is natural number. And the second example same, so the second example is fn x is equal sin nx by n is here. So you observe n is 1, sin x by 1x by 1 is here, and f2 x equal sin 2x by 2 and f3 x equal sin 3x by 3, f4 x equal sin 4x by 4. This is a sequence of functions can be taken. Similarly, we define fn x equal 1 minus mod x power n, and where domain x is the open minus 1 comma 1 is here. And the fourth example, fn x equal to n into x power n. You see the in this example f1 x equal 1 into x power 1, f2 x equal 2 into x square, f3 x equal 3 into x power 3 dash dash can be taken. And similarly we define fn x is another definition, and cos x power n is here. f1 x is equal cos x power 1, f2 x equal cos x whole square. And this is the this way definition of the sequence of whatever is here functions can be taken is here. This is a function. Right. So next, if sequence of functions is defined, is here, then the whatever the in sequence of numbers we defined the convergent divergent can be taken. Same concepts, right, is also we observing is here in the sequence of functions can be taken. Right. So Narendra sir, explain how convergent of functions can be taken.
Yes sir.
Yeah.
Suppose fn of x is sequence of functions. Suppose if we fix x, that means some, for example, fn of x is equal to x to the power of n, n belongs to n, x belongs to closed interval 0 1. Suppose if fix one x in this domain, x belongs to closed interval 0 1. Suppose if you take x is equal to 1 by 2, then fn of 1 by 2 which is equal to 1 by 2 whole to the power of n, which is equal to 1 by 2 power n. This is the sequence of real numbers. If we fix x, then fn of x is sequence of real numbers. Already in the last class we had discussed about the sequence of real numbers. Now suppose here 1 by 2 power n, this sequence is converges to 0. Suppose if you take x is equal to 1 by 3, then fn of 1 by 3 is 1 by 3 whole to the power of n, which is equal to 1 by 3 power n, which is also converges to 0. That means if we fix the x value, then fn of x is a sequence of real numbers. Now we can discuss about this one. Now suppose if you take x is equal to 0, then fn of 0 is 0. This is a constant sequence which is converges to 0, and fn of 1, which is 1 sequence of real numbers, which is a constant sequence which is converges to 1. In this case, the sequence, if we fix x, fn of x converges to either 0 or 1. Now 0 if 0 less than or equal to x less than 1 in this case, and if x is equal to 1, then fn of x converges to 1. In this case we say that fn of x is said to be converges to 0. Now if 0 less than or equal to x less than 1, and if x is equal to 1, fn of x converges to 1. So now suppose if in the previous one fn of 1 by 2 is equal to 1 by 2 power n, we know that which is converges to 0. That means by the definition of convergent of a sequence, for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod fn of 1 by 2 minus 0 less than epsilon. So this is a sequence of convergent of sequence of real numbers. Suppose if we fix x, that means fn of x is sequence of real numbers if which converges to suppose some f of x, then by definition for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod fn of x minus f of x less than epsilon. Suppose if you take x belongs to yes or here 0, close interval 0 1, then fn of x is converges to f of x. Here point wise means we fix x means ఒక్కొక్క పాయింట్ సబ్స్టిట్యూట్ చేసుకుంటూ వెళ్తున్నాం కాబట్టి, then we say that fn of x converges to f of x point wise on the domain here x belongs to close interval 0 1. Next
right. So thank you, Narendra. So first the sequence in the sequence of real numbers, only convergent or divergent are there. In the sequence of functions is here, the two type of convergent can be taken. So for fn is the sequence of functions is here, so different x values, x coming from the domain, right, we substitute different values is here, we get the different the sequence of real numbers is here. So fn is convergent for each point of the x belongs to the domain, then that convergent is called the point-wise convergent of the sequence of functions can be taken. So how defined mathematically the whatever the point-wise convergent can be taken. So suppose the fn, the convergent of the function fn convergent to the function point-wise convergent to the function f of x is here. For each the error epsilon greater than 0, the and for each point of x belongs to x is here, there exists number n such that mod fn x minus fx less than epsilon for every n greater than n is here, then that convergent is called the point wise convergent is here, and we write limit of fn x is equal to f of f point wise on s is here, or fn to f point wise on s can be taken is here. So చూడండి విద్యార్థులారా, రైట్, మనం వాస్తవ సంఖ్యల యొక్క అనుక్రమం తీసుకున్నప్పుడు అభిసరణ లేదా అపసరణ గురించి మాత్రమే డిస్కషన్ చేస్తాం. ఇక్కడ ప్రమేయ అనుక్రమాన్ని గురించి మనం మాట్లాడుతూ ఉన్నప్పుడు, సో fn అనేది ఏదైనా ఒక ప్రమేయం అనుక్రమం తీసుకున్నప్పుడు, రైట్, దాని యొక్క ప్రదేశం ఎస్ అనుకుంటే ఎస్ లో ఉన్న ప్రతి బిందువు దగ్గర కూడా fn ఎక్స్లో ఉన్న ఎస్లోని ప్రతి బిందువు దగ్గర కూడా ఎఫ్ఎన్ అనేది వాస్తవ సంఖ్యగా మారిపోతుంది, వాస్తవ సంఖ్య అనుక్రమంగా మారిపోతుంది. అట్లా ఎస్లోని ప్రతి బిందువు దగ్గర కూడా ఎఫ్ఎన్ అనేది అభిసరిస్తే దాన్ని బిందుపర అభిసరణ అంటాము. రైట్. ఆ అభిసరణ అనేది ఎఫ్కి అభిసరిస్తే దాని లిమిట్ ఆఫ్ ఎఫ్ఎన్ ఇజ్ ఈక్వల్ టు ఎఫ్, ఎస్ పై బిందు పద అభిసరణ అంటాము. లేదా ఎఫ్ఎన్ టు ఎఫ్ పాయింట్ వైజ్ కన్వర్జెంట్ టు ఆన్ ఎస్ అంటాం. ఎస్ పై ఎఫ్ఎన్ టైమ్స్ టు ఎఫ్ అనేది బిందు పద అభిసరణ అంటాం. అంటే ఎస్లో ఉన్న ప్రతి బిందువు దగ్గర కూడా ఎఫ్ఎన్ ఎక్స్ అనేది వాస్తవ అనుక్రమం అవుతుంది. ప్రతి ఎఫ్ఎన్ ఎక్స్ అనేది కూడా ఎఫ్ ఆఫ్ ఎక్స్ అనే వాస్తవ సంఖ్య అభిసరిస్తుంది. రైట్. సో దీని నుంచి మనకు ఏంటంటే మన వాస్తవ సంఖ్యలలో కూడా ఒకే రకమైన అభిసరణ ఉంటుంది. కానీ ఈ ప్రమేయానుసారానికి వచ్చే వరకులా రెండు రకాలైన అభిసరణలు ఉంటాయి. మొదట బిందుపర అభిసరణ గురించి డిస్కషన్ చేస్తా ఉన్నాం. సో మొదట ఫస్ట్ ఎగ్జాంపుల్లో ఎఫ్ఎన్ ఎక్స్ ఈక్వల్ టు ఎక్స్ పవర్ ఎన్, ఎక్స్ బిలాంగ్స్ టు క్లోజ్ 0 1 చూసినప్పుడు రైట్. సో నరేంద్ర సార్ ఆల్రెడీ ఎక్స్ప్లెయిన్ చేసినాడు. ఎక్స్ బిలాంగ్స్ టు క్లోజ్డ్ 0 ఓపెన్ 1 అయినప్పుడు మనం అంతా కూడా ఎఫ్ఎన్ ఎక్స్ అనేది కూడా 0కి అభిసరిస్తుంది. ఎక్స్ ఈక్వల్ 1 అయినప్పుడు ఎక్స్ పవర్ అనేది ఒకటికి అభిసరిస్తుంది. కాబట్టి ఎఫ్ఎన్ ఎక్స్ ఈక్వల్ ఎక్స్ పవర్ ఎన్ అయినప్పుడు లిమిట్ ఎన్ టైమ్స్ టు ఇన్ఫినిటీ ఎఫ్ఎన్ ఎక్స్ ఈక్వల్ ఎఫ్ ఆఫ్ ఎక్స్. ఇక్కడ ఎఫ్ఎక్స్ అనేది 0. అప్పుడు ఎప్పుడండి ఎక్స్ బిలాంగ్స్ టు క్లోజ్డ్ 0 ఓపెన్ 1 అయినప్పుడు రైట్. ఎక్స్ ఈక్వల్ 1 అయినప్పుడు 1. ఇక్కడ చూడండి ఈ ఉదాహరణలో బిందుపద అభిసరణ ఉదాహరణలో మొదటి ఉదాహరణలో ఎఫ్ఎన్ ఎక్స్ ఈక్వల్ ఎక్స్ పవర్ ఎన్, ఎక్స్ బిలాంగ్స్ టు క్లోజ్ 0 1 తీసుకుంటే సో ఆల్రెడీ సార్ ఎక్స్ప్లెయిన్ చేసిన దాని ప్రకారం లిమిట్ ఎన్ టైమ్స్ టు ఇన్ఫినిటీ ఎఫ్ఎన్ ఎక్స్ ఈక్వల్ ఎఫ్ ఆఫ్ ఎక్స్. ఇక్కడ ఎఫ్ఎక్స్ అనేది ఎక్స్ బిలాంగ్స్ టు క్లోజ్ 0 ఓపెన్ 1 అయినప్పుడు 0 అయింది, ఎక్స్ ఈక్వల్ 1 అయినప్పుడు 1 అయింది. కాబట్టి ఎఫ్ఎన్ అనేది ఎఫ్కి బిందుపద అభిసరణ చెందుతుంది. రైట్. ఇప్పుడు సెకండ్ ఎగ్జాంపుల్ సార్ ఎక్స్ప్లెయిన్ చేస్తారు. సార్ చూడండి నరేంద్ర సార్.
Thank you, sir. Here fn of x is equal to sin x by n, x belongs to R, n belongs to n. Suppose if you take any x in R, suppose if you take x is equal to 1, then fn of 1 is here sin n by n. That means here fn of 1 is equal to sin n by n. Here sin n by n, we know that minus 1 less than or equal to sin n less than or equal to 1. Here minus 1 by n less than or equal to sin n by n less than or equal to 1 by n. Here n belongs to n. So we know that 1 by n is converges to 0. Minus 1 by n is also converges to 0. By sandwich theorem, we know that sin n by n is also converges to 0. If x is equal to 1, then fn of 1 is sequence of real numbers, that is the sin n by n, which is converges to 0. At this point this is converges. Now we have to check at each point in R. In generally we can write as minus 1 less than or equal to sin nx by n, sin nx less than or equal to 1. Here by n means here also n belongs to n. So by sandwich theorem, which converges to 0, which is also converges to 0, so which is converges to 0 for every x, therefore fn of x converges to 0 for every x in R. Therefore here limit fn of x n tends to infinity is equal to 0, or we can write fn converges to 0 point wise on R. Thank you, sir.
Right. So the Narendra sir explained. Right. Second example, sin nx by n is here. Fnx equal. So you observe f1x equal sin n by n, f2x equal sin 2x by sin 2n by n, and the f3x equal sin 3n by n, and the f4x equal sin 4n by n. Using the right nice sandwich theorem, right. So explain the whatever the how to convergent. You take any x is here, the fnx convergent to 0. That's why so the sequence fnx convergent to the point wise to the function f of x equal 0 can be taken. In the third example, fnx equal 1 minus mod x power n, where x belongs to the open 0 1 is here. So here is also we observing is here, right. X belongs to open 0 1 is here, and the 1 minus mod x is also less than 1 is here, and the 1 minus mod x is also less than 1 and positive is here. So and also we observe is here a lies between 0 and 1. then a power n convergent to a power n convergent to whatever is here 0 can be taken. And also we observe here particularly x is equal 1 we substitute fn 1 is equal 1 minus 1 is here 1 minus 1 is equal to whatever is here 0. That is why limit n tends to infinity fn x equal to f of x is here, where fx is equal if x not equal to 0 and x equal 0 we substitute is here, the value is equal to 1 is here, right. That is why if what the domain is open minus 1 comma 1 is here, we substitute all points from open minus 1 to 1 is here, substituting x equal 0 the convergent to 1 is here and other points convergent to whatever is here 0, and fn is convergent at each point can be taken. That is why, so the fn convergent to point wise to the function f of x is here, where f of x is equal the whatever the x is not equal to 0 and x equal 0 the point wise convergent x equal 0 the value is 1 can be taken is here. So that is why the function fn x convergent to the point wise convergent to the function f of x can be taken. And the my Narendra sir explained the fourth example with demonstration.
Suppose here in fourth example fn of x is equal to n into x to the power of n, x belongs to closed 0 open 1 and n belongs to n. In this case here x belongs to closed 0 and open 1. Hence suppose if you take one x value, particular x value in this interval, x is equal to, suppose if you take 1 by 2, then fn of 1 by 2 which is equal to n into 1 by 2 power n, we know that which is converges to 0 as n tends to infinity. In generally here fn of, for any x fn of x converges to 0 as n tends to infinity. So limit fn of x n tends to infinity is equal to 0. In this case we say that fn of x is pointwise converges to f, that means 0. fn of x is pointwise converges to 0 on the closed interval 0 and open 1. Now
Right. Next examples, right. What about the next examples? We last the 4-5 examples we see the, so what is the pointwise convergent, right. All of the examples are pointwise convergent into the given domain. Now we see that you see the first example fn x equal to x power n, x belongs to closed 0 comma 2 is here. Suppose you substitute 2, right, then what happen is here fn 2 is equal to 2 power n. What is the 2 power n? 2 power n goes to infinite, not go to finite. That is why divergent can be taken. Okay, you substitute in this domain, the all points can be taken at 2, the divergent can be taken. The substitute 0, 0 is the 0 power n is also convergent to 0 is here. So substitute 1, 1 power n is also convergent to 1, that is no problem. But substitute 2 is here, not convergent. And what happened? Fn is the sequence of function. At some points in the domain convergent and some points is not convergent is here, then that convergent is not a pointwise convergent can be taken. If convergent at every point in the domain, then that convergent is called pointwise convergent. And that not convergent at some points is here, then that convergent is not a pointwise convergent can be taken. You have a example. Suppose in the first example take the x equal 1.5. 1.5 power n is also infinite can be taken is here, and 1.8 is also our domain is also infinite can be taken is here. That's why, so the function definition fn x equal to x power n, where domain x belongs to closed 0 comma 2 is not pointwise convergent can be taken. And similarly second example also can be taken fn x equal to n into x power n, x belongs to closed 0 comma 1 is here. So this is also not a whatever is here pointwise convergent can be taken is here, right. These two previous examples are pointwise convergent and these examples are not pointwise convergent. Why not pointwise convergent? You substitute in the domain, some points can be taken is here. So the sequence of numbers are not convergent is here. That's why, so this convergent is not a pointwise convergent. చూడండి విద్యార్థులారా, సో ఇంతకుముందు మనం కొన్ని ఉదాహరణలు అబ్జర్వ్ చేసినాం. సో fn అనేది ప్రమేయానుక్రమం, ఆ ప్రమేయానుక్రమంలో x అనేది ప్రదేశంలోని ప్రతి బిందువు దగ్గర కూడా ప్రతి బిందువు x బిలాంగ్స్ టు s దగ్గర, సో ఆ fn x అనేది అభిసరిస్తే దాన్ని బిందుపద అభిసరణ అన్నాం, రైట్. కానీ ఏదైనా ఒక x బిలాంగ్స్ టు s వద్ద fn అనేది అభిసరించకపోతే దాన్ని బిందుపద అభిసరణ కాదు, అపసరిస్తుంది అంటాం, right. Next one, so what is the next in the advanced section is here. So after the pointwise convergent, then how the uniformly can be taken. So Narendra sir explain the what the uniform convergence is here.
Sir, thank you sir. Suppose we know that what is the pointwise convergence. Pointwise convergence means, suppose fix x, then fn of x is sequence of real numbers. If it is converges for each x, then fn of x is pointwise converges. Now what is that meaning here? For any fixed x, then fn of x is sequence of real numbers. That suppose it is a pointwise convergence means fn of x converges to f of x pointwise on domain S. That means for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod fn of x minus f of x less than epsilon. In this case, n depends on epsilon. What is x here? X. That means n depends on x and epsilon. Suppose if n depends only on epsilon, then this converges is said to be uniform converges. That means for each epsilon greater than 0, for each epsilon greater than 0, and there exists a number n which depends only on epsilon, such that mod fn of x minus f of x less than epsilon for all n greater than n, x belongs to S. Now in this case here, n depends only on epsilon, then fn of x converges to f of x uniform on S. This is mathematically definition. Upendra sir explained in general.
Right. So, Narendra, thank you, Narendra sir. Right. What about the first point-wise convergent? Point-wise convergent means Fn, right, Fn is the sequence of functions convergent to every point can be taken, convergent to the f of x can be taken. So, this the convergence, right, we substitute different points is here, you convergent to the different function. If this function, right, is not in general, right, only you substitute any point can be taken is here. So, fx is same can be taken, then that is called the uniform convergence can be taken is here. So, whatever is here in the definition, uniform convergence is here. So, fnx mod fnx minus f of x less than epsilon, for all points you take any point of x belongs to x is here, and for all n belongs to n is here. So, this value right, estimation between mod fnx minus x is very small can be taken is here, then that convergent is called the uniform convergent can be taken. Main difference between point-wise convergent and uniform convergent is here. Point-wise convergent means at each point x belongs to S, Fn is convergent to some function can be taken, right. Whatever the different points can be taken, different points of x is here, fnx convergent to the same value can be taken, same function f of x is here, then that convergent is called the uniform convergent can be taken. Then this we write is here, limit of fnx equal to f uniformly on S, or fn times to f uniformly on Sn can be taken. You see the first example, fn x is equal to sin nx by n is here. You substitute the whatever is here, n is equal to x equal 0 you substitute, or n is equal 1, alright, or the x is any real number can be you substitute is here. So, x1 we substitute, x2 substitute, x3 substitute, x4 substitute, x100 substitute is here, all are convergent to whatever is here 0. In general, mod sin nx by n less than or equal to 1 by n is here, right. So, you substitute any x value can be taken is less than or equal to 1 by n convergent to 0 is here, that is why this convergent is the uniform convergent can be taken, right. Main difference between point-wise convergent and uniform convergent is here. Uniform convergent you take any x is here, the value directly depend upon only n, not x can be taken is here, and the Narendra sir explained detail in the second example is here. Sir.
you, sir.
Alright. So, in the you see the here first example is also can be taken. Epsilon is any positive and n is equal to 1 by n we estimate. Mod fnx minus 0 is here. Right. Mod sin nx by n is here. So, we know that the sin nx is always less than or equal to 1 and the mod sin nx by n less than or equal to 1 by n, and already we selected the n greater than n, 1 by n is less than epsilon, that is why. So, according to the definition Fn tends to 0 uniformly convergent on R can be taken is here, and the Narendra sir explained the second example.
Thank you, sir. In second example, fn of x is equal to n into x to the power of n, x belongs to closed 0 open 1 and n belongs to n. Already we have discussed about pointwise converges on this example. Here fn is converges to 0 pointwise on closed interval 0 and open 1. Now, is it uniform converges or not? We have to check now. Now, suppose here example is fn of x is equal to n into x to the power of n, n belongs to n, x belongs to closed 0 open 1. So, here fn converges to 0 pointwise converges on closed 0 open 1, we know this one. Now, is it uniform converges or not? Uniform means by definition for each epsilon greater than 0 there exists a number n such that mod fn minus 0 less than epsilon for all n greater than n and x belongs to here closed 0 open 1 from this for this example. If assume fn converges to f or 0 uniform converges, which is true for all epsilon greater than 0. Therefore, let us suppose epsilon is equal to 1 or 1 by 2 some epsilon is equal to 1. For epsilon is equal to 1 also there exists a number n such that mod fn means n into x to the power of n minus 0 less than epsilon means here 1 for all n greater than n and x belongs to closed 0 open 1. So, here n is natural number, x belongs to n is natural number, x belongs to closed 0 open 1, therefore, this is a positive, hence it can be written as n x to the power of n less than 1, where x in x belongs to closed 0 open 1. Now, suppose in particular here n greater than n means, suppose if you take n is a natural number, suppose in particular capital N plus 1 into x to the power of n plus 1 is less than 1. Suppose if you take x in 0 and 1, if assume that x is equal to 1 by n plus 1 whole to the power of n plus 1, which belongs to closed 0 and open 1. So, now here it can be written as x to the power of n plus 1 is equal to 1 by n plus 1. Hence, from this one n plus 1 into x to the power of n plus 1 is equal to 1, but here n plus 1 into x to the power of n plus 1 is less than 1. Here n plus 1 into x to the power of n is equal to 1. Therefore, for this x which fails, that means which fails the converges is uniform. For this example, fn of x is equal to n into x to the power of n, n belongs to n, x belongs to closed 0 open 1 is not uniform converges to 0. sir.
Right. Thank you, Narendra. Right. Sir, clearly explain the fnx is equal, second example, fnx is equal to n into x power n, x belongs to closed 0 open 1. Already we see that this is the pointwise convergent but not uniformly convergent is here. Why? Take we controversial example is here. Put the, let epsilon is equal 1 is positive. Right, according to the definition, mod fnx minus fx estimate. So we value is the that value is here. In particular, take n plus 1 into x power n plus 1 is less than 1. So we get the controversion. That's why. So this convergent is not a uniformly convergent is here. So only this is pointwise convergent, but not the uniform convergent is here. Why? The particularly we put the one of the substitute the value is here. So our estimation is not less than 1 is here. So that's why the convergent is not a uniform convergent is here. So every time the what happen is here, suppose fn is the given definition, right? How we decide the pointwise convergent or uniform convergent is here. Every time estimation is complicated. So what is the criterion to decide the uniform whether uniform convergent or pointwise convergent is here? So in this direction, right, first we study the one of the theorem is here. So what is the theorem is here? The uniform limit continuous the theorem function can be taken. What happen? Fn into f is uniformly convergent on s is here. If each fn is continuous function on s, then f is also a continuous function is here. Fn is uniformly continuous function and each fn is continuous function, then the uniform limit function f is also a continuous function on s is here. So Narendra sir explain this theorem is here.
Thank you, sir. Here each fn is continuous on the domain. Fn uniform converges to f, then f is continuous also. Suppose here fn converges to f, uniform converges on s for each, and for each n fn is continuous on s, then f is also continuous on s. That means f is continuous on s means f is continuous at each point. Fn is continuous on s means fn is continuous at each point of s. Suppose if fn is continuous at x naught in s, here x naught in s, each fn is continuous and fn converges to f uniform on s. That means for each epsilon greater than 0, formal definition, there exists a number or natural number, there exists natural number n or general number n such that mod fn of x minus f of x less than epsilon for all n greater than n and x belongs to s. Now here n greater than n means, suppose here we know that what about n here, fn plus 1, here n is a natural number, fn plus 1 is, n plus 1 is a natural number, fn plus 1 is also in particular is continuous from given, fn plus 1 is a continuous function at x naught, here from this one at x naught. Therefore by formal definition of continuity, for this epsilon there exists a delta greater than 0 such that mod x minus x naught less than delta, that implies mod fn plus 1 of x minus fn plus 1 of x naught less than epsilon. Now here x belongs to s. We know that by f of x minus f of x naught can be expressed as mod f of x minus fn plus 1 of x plus fn plus 1 of x minus fn plus 1 of x naught plus fn plus 1 of x naught minus f of x naught. So, it can be expressed as which is less than or equal to mod f of x minus fn plus 1 of x plus mod fn plus 1 of x minus fn plus 1 of x naught plus mod fn plus 1 of x naught minus f of x naught. Now, in previous already we discussed about here fn of x minus f of x less than epsilon for all n greater than n x belongs to S. Epsilon means here in this one f of x minus fn plus 1 of x for each, in this case particularly n, if n is equal to n plus 1, this value is which is less than epsilon. Now, here fn plus 1 is the continuous, from this one fn plus 1 of x minus fn plus 1 of x naught less than epsilon, therefore, which is also epsilon plus, now here in particular here at n is equal to n plus 1 and x is equal to x naught, here also which is also less than epsilon. So, in formal definition, or it can be written as here mod f of x minus f of x naught which is less than 3 epsilon, which is also, or it can be written as in this way fn of x minus f of x less than epsilon means we can take epsilon by 3, here also epsilon by 3. From this one we can write here epsilon by 3, here epsilon by 3, epsilon by 3, then we get which is equal to epsilon. That means for each epsilon greater than 0 from starting onwards, there exists a delta greater than 0 such that mod x minus x naught less than delta x belongs to S, that implies mod f of x minus f of x naught is less than epsilon, which shows that f is continuous at x naught. Here x naught is arbitrary on S, therefore, f is continuous on S. That means, if for each n fn is continuous at x naught, then f is continuous at x naught. If each n fn is continuous on S, then f is continuous on S if fn converges to uniform f on S.
Okay, thank you Narendra sir. So, the suppose fn tends to f is uniformly convergent on S is here, each fn is continuous function, then f is also a continuous function on S is here. So, mainly using here, suppose each fn is continuous function, but f is not continuous function, then this uniformly convergent is a only pointwise convergent, but not uniformly convergent is here. So, see the example is here, fn x is equal to x power n is here, we see that the fn is convergent to the pointwise to the function f of x is here. Here fx is defined, here fx is not continuous at x equal 1 is here. So, that is why this convergent is only pointwise, not uniformly convergent can be taken. Here each fn is continuous function, f is not a what is the continuous function. In the second example is also can be taken fn x equal 1 minus mod x power n is here, convergent to the pointwise to the function fx is here, where fx equal 0 and 1, 0 is x is not equal 0, 1 if x equal 0, but each fn is continuous function, but f is not continuous function is here. So, this is why this convergent is also a pointwise convergent, but not uniformly convergent can be taken is here. And also another theorem also there is here. Next class we discuss the how prove the most importance of the uniform convergent can be taken is here. So, in this class we discuss the what is the sequence of functions definition, and the how many types of convergence can be taken is here. Pointwise convergent and uniform convergent is here. So, what are the main difference, and the first one of the theorem we using here, each fn is continuous function, then f is also a continuous function can be taken, and myself and Narendra sir so explain this one. Thank you very much the students, right. This is a very important topic of the in degree second year. So, you study the perfect one, this is the most important topic in third unit is here. So, you right, best of luck the student, my sir Narendra sir, right. Thank you very much sir, thank you sir.
Thank you, sir.
Thank you sir.